Greetings to all you students of the internet, and thank you for feedback. And that is evidence enough that at least some of the work is being interacted with. Now, I've kept mixing the learning sessions because I have a few different groups, but I hope that for my slowest group, the youngest group, those who are doing a level 3 and level 4, you're following this keenly, and by the time you get to now the second unit of solar installation, all these concepts will be in your mind, and so you'll have an easier time learning. So those outside Butere Technical, apologies for the mix-up of content. But I hope we'll learn how to do this the right way, and we'll have enough time to just film the same learning sessions consecutively until we have exhausted a unit, and then we go to the next unit like that, hopefully. So today, let's expound on the charging profiles. So by the end of this session, I want you to write this down so that by the end of this session, you'll have at least captured or understood why charging profiles will affect the performance of battery. So I'll focus on the lead acid, the flooded lead acid battery after this, and we shall look at the other battery types briefly, just enough to introduce you, and then probably you can do your own research after this. Now, this is a follow-up now on the previous session about communication protocols. I'll share an image somewhere here of Taiko. Taiko sent me their latest product catalog, and they have included at least a variety of the inverters now do have both the RS and the CAN bus communication protocol. So that is why I'm teaching this, so that students can understand there is a relationship between the charging profile, the component configuration, and the charging profile, component configuration, and the communication protocols that these components will utilize. Now, a charging profile is a dynamic, intelligent process where components within the solar system communicate to ensure the following. Number one, at any given point, the maximum energy from the charging source is harvested and utilized. So the charging source, in this case, because most of our students, because we are dealing with this unit was supposed to deal with the standalone solar PV system. So the charging source here will be limited to the sun. But for students who are doing both the grid type systems or the hybrid systems, depending on how you want to categorize them, the charging source could either be the sun, which is number one, or the main charging source, or it could be the grid. There are people who have inverters that are connected to the grid, so they don't have solar panels, they just have an inverter and a battery bank. So the inverter charges the battery bank when the grid is available, and when the grid is not available, the reverse happens. So there are people who have got these systems and they utilize them in that manner. Or there are people who have generators or wind turbine, the diesel or the diesel powered generators, or even the petrol powered generators, wind turbines. There are people who have wind turbines, and even various sources of energy. So a good charging profile is supposed to ensure that at any given point, the maximum energy from the charging source is harvested and utilized. And what I mean by this is that maximum energy means that the maximum amount of voltage and current that is being delivered by the energy source is being sent to the battery. The battery, it could be one, it could be a pack, it could be a bank, whichever. Now, number two, a charging profile is supposed to ensure that the batteries are fully charged within the time frame allowed. So the time frame allowed will now be based on several other parameters, and I think I've mentioned this lightly. So there are some batteries that can charge within 4 hours, 6 hours, or 12 hours, and that depends now on something called a C-rate. C-rate here. So different battery designs have got different battery C-rates, and we can also talk about it later on, just briefly. The charging profile is supposed to ensure that the batteries are safely maintained when full to achieve longer lifespans. So A charging profile is not just also about charging, it's also about ensuring that if the battery is fully charged, the state of charge is at 100%, the battery is maintained safely at 100%, and we shall explain how that happens and why it's important for the different types of batteries. So essentially, a charging profile is a program, is a programmed way of ensuring that the charger, it could be the independent charger, it could be the PWM, it could be the MPPT, it could be an inbuilt charger within the all-in-one inverter component, whichever charger. It's just ensuring that the charger supplies the voltage and current in predetermined values during the charging cycle of a battery. And these predetermined values are essential during the charging cycle, and our next learning session is about now the different values depending on what stage of the charging cycle the battery is. So the charging profiles differ with the following. Number one, the chemistry. So the charging profile of a lead acid battery is different from even with the lead acid battery, the different sub designs. We've got the flooded, we have got the gel, whichever design, the AGM, the so when you change the chemistry between lead acid to lithium, you are also supposed to change the charging profile in or the program that controls the charging profile in the charger. So when you are dealing with the lead acid battery, the charging profile is different. When you're dealing with the lithium battery, the charging profile is different. When you're dealing with the nickel cadmium battery, the charging profile is different. But for us, for most of the students that we are teaching, we will look at the lead acid and the lithium ion batteries. The internal architecture of the battery, the charging profile will differ with the internal architecture. So this is also important because the internal architecture of the battery keeps changing with, depending on the manufacturer. Some manufacturers are becoming more and more advanced, and so the charging profile, for example, of a cylindrical or a pouch. We have got the cylindrical one, the pouch one. We have got several internal architectures, and this internal architecture is also related to how each cell has been connected to the other, how they have been designed. Technically, the structure of the cells. Some cells are rectangular in nature, longer. Some are square in nature. Some are in cylinders. So the different internal architecture will also determine the charging profile. And then the size of the pack. The size of the pack means, for example, you have got a lead acid battery that is 12 volts, 100 Ah. That is both the capacity and the voltage. And then another system has got the same 12 volt battery, but let's say 400 Ah. And another system has got the same 12 volt battery, but let's say 1000 Ah. So the capacity will affect the design or the program in the charging profile that you'll use in your charger or in your yes, in your charger or in your charge controller. And then the temperature also affects the charging profile. So we have mentioned it, how temperature affects battery performance, and this is one. The C rate we've mentioned, the state of charge. The state of charge, we also mentioned that we say that, for example, if a battery could be displaying 14.2 volts, but the state of charge is not at maximum or 100%. This battery could be displaying 14.2 volts, but the state of charge is as little as 60%. So if the inverter or the charge controller is not capable of determining the difference between the voltage level and the state of charge, it might stop charging. So we shall also expound on this further for students to understand. And then battery health, the state of the health. So the state of the health basically means that if, for example, your battery has been in use for, let's say, 4 years, the way the chemical reactions have occurred within the battery, because a battery is a chemical structure, the internal structure has got chemical components that hold and release charge when they're required to. So after some time, there are some chemical reactions that normally happen within that battery that affect how it will, the density now of the charge that it can hold. So after some time, it becomes weaker. The battery, the state of health will be at 100% when the battery is still new, but it will keep losing slowly by slowly. So if your charge profile is not programmed to understand that the state of health of the battery is deteriorating, it might keep treating this battery as a, like with the predetermined programs that are meant to serve a very new battery, which also mean that it will either be punishing it or underutilizing it, or either punishing it with the excess values, probably in voltage and current, or underutilizing it, or under charging it with the lower voltages and lower currents. So next, let's understand the different stages of a charging profile. A charging profile is broken down into three main stages. So let's look at them, and these three stages now will open up how the different battery types are affected. So in most systems, in most solar PV powered systems, batteries utilize the three stages of a charging profile. Most of these systems utilize these three stages for a charging, for a complete charge cycle to happen. Now, the first stage is normally called the bulk stage or the constant current stage. This is the first stage where we begin it, and I'll explain here. And say the second stage is the absorption stage or the constant voltage stage, and then the third stage is the float stage. And then for very specific battery types, for example, in lead acid batteries, we have got a stage called equalization stage, and we shall explain it later. So first, let's define these three stages first. In the bulk stage, in most cases in the bulk stage, a good example is when the SOC is at its lowest point. So for example, in our systems, in most common systems, you'll find that the SOC during in the early hours of the morning, because the system has been utilized overnight, the state of charge is at its lowest point. If you size the good system, you'll find that the SOC, for example, in lead acid, the lowest will be around 50 or 60% state of charge. So the bulk stage normally happens from the lowest point of the battery pack and raising the SOC to around 80 or 90%, depending on the battery type. So in most cases it's 80, in some cases it's 90%. So when the first charging stage, where the system picks the maximum amount of power from whichever source and raises the battery state of charge from the lowest, probably 20 in lithium ion or 30, to around 80 or 90%, that stage is normally called the bulk stage. And in this stage, high current is used to raise the battery voltage. So in this case, you might find the battery voltage, for example, from, if it's a 12-volt system, you'll find the battery voltage is around 11.6 or 11.7. Like it's normally at the lowest. In a very good system, it's at the lowest stage, but not zero. So in some charging systems, this is how the bulk stage happens. In the very basic systems, like the standalone system where you just have a panel, a PWM charge controller, and a battery, in that case, because we are not really, most PWMs are normally primitive. They don't really bother understanding what is happening. They just pick whatever power the panel is generating and smoothen it or lower it to the respective capacity and then release it into the battery. So in that case, we can say that that stage normally happens between the early hours of the morning to around 2 p.m. So the other parameters are not really taken into account for such a system, for the primitive system. So there's no communication, there's no nothing. But in some systems, the smarter systems, there are inverters that are got way improved features and that can allow a lot of interaction between the power source, the several power sources, the battery pack, the loads. So these inverters have got bigger brains, and so the inverter can, when we did load profiling, I explained something a little bit. So the inverter, with its inbuilt charge controller, can say, because it's, for example, 8 a.m. in the morning or 9 a.m. and I'm not receiving maximum power from the sun, and this inverter has got internet access. So that we have inverters that have been configured to connect to the Wi-Fi and internet access. So the inverter can pick that. So the inverter can pick data from the internet, from specific sources, and say, because it's 8 a.m. or 9 a.m. and the sun is, according to the weather prediction, there will be maximum sunlight during the day. So I've got no worry about charging, about utilizing power from the sun in charging my system. And then the same inverter will monitor the system, and then during the day, probably there's a, let's say there's a change in weather, or not weather, because we had already fed it weather. So let's say during the day, a load is added into the system, and you remember this inverter has been on that system for quite a while, so it has got enough memory to understand that probably because today is a Tuesday, this is how this client normally consumes power. So inverters that have got bigger data sets to work with, so it might listen to the load profile and say, it's a Tuesday, and they've plugged in something that they normally don't plug in at this time. So it goes back to its data and realize, on Tuesday, we normally consume this amount of power from the batteries, but it's 4 p.m. or it's 3 p.m. and they've plugged something that they normally don't plug in. So that means that if I utilize the power in the batteries, when now the usual loads will be plugged in, I might not have enough to run all the way to the next charging cycle. So what do? It reads whatever the panel is generating, it looks at the time, it looks at the weather forecast, and then it also looks at the grid and realizes that, give or take, probably there's enough sun, but because this load is too big, what do? Let me pick from the grid and feed this load directly. Or let me pick from the grid and charge my batteries. That is just an overview of now how communication protocols happen. So for such inverters, which are way more advanced, they will utilize multiple power sources to achieve this bulk stage, depending on source availability. So even this same inverter, if it realizes that it's early in the morning, and it's too cloudy and the state of charge is way too low, this inverter won't wait for the sun to come up. It might read the weather forecast, or it might just decide, because there's no enough sunlight at this particular hour, and I need to boost the state of charge in my batteries. What do? Pick from the grid. It will be picking intermittently. It could decide to pick completely or intermittently from the grid and from the panels. So if the panels are generating above a certain category, it says, let me use whatever is being generated from the panels, bypass it to the loads, but pick what is from the grid, because the grid is constantly supplying. Let me pick from the grid and do this bulk stage. That is just an overview, an example. And we've also said the load profile of the day. So some inverters will also listen to the load profile. If they realize that you've plugged in something that is normally not plugged in at that particular moment, they change the characteristics of how they do the charging or the discharging. And not even on the bulk stage, but in general, some inverters will listen to the load, the grid, the solar, all these parameters, and they make decisions based on that. But those are the way advanced inverters, not the basic inverters. So the next stage, let's look at the absorption stage. So this bulk stage, this one is utilized by almost all systems. Lead acid batteries, lithium batteries, nickel, almost all of them will utilize the bulk stage. So let's go to the absorption stage. So we have moved from the bulk stage, the constant current stage, and we have We've now charged our battery from the lowest state of charge to around 80 or 90%. So in a smart system or the advanced systems, once the charge controller or the inverter notices that now this battery is at a higher state of charge, 80 or 90, depending on the battery type, it changes now. It stops sending in maximum current and it just ensures that it is sending in a very small amount of current to ensure that now the battery, because a battery pack has got several cells, it's not just one cell. And at some point, I explained that a battery could be reading 14.4 volts for a 12 volt system or a 12 volt battery. But that 14.4 volts could not be the true voltage. So a battery has got a 12 volt system, for example, is normally a pack on the outside, but on the inside, we normally have small subsections that so we have got cells, and then those cells now make up the battery. So for example, for a 12 volt system, we might have 6 cells, for example, and each cell carries 2 volts. It normally varies depending on the system. So in some case, you might find that for a 12 volt system, the maximum value that a 12 volt system is supposed to hold for it to be considered fully charged is 14.4 volts. So when the battery is displaying 14.4 volts, in some cases you'll find that the individual cells, not all of them are at their maximum for the battery to read 14.4 volts. So you might find that some of the cells, for example, if you divide 14.4 by 6, you might find that each cell is supposed to carry around 2.4 volts. Now, you'll find that in a system that some of the cells will have charged to 2.4, some will even have overcharged to around 2.6, and some are still as low as 2.2 or 2 volts. So for this battery to ensure that all these cells now, all of them, those that are below 2.4 go to 2.4, and those that are above 2.4 discharge to 2.4, the system will keep sending a small amount of current to ensure that the battery stabilizes and all the cells are at the same voltage. So what this means is that you just send enough to ensure that those that have not yet fully charged keep rising up, and those that have overcharged, those that have overcharged will now start releasing some of that charge to the less charged batteries. So it normally varies. The actual technical structure normally varies depending on the battery type. Those that are overcharged in some systems will be forced to release to the less charged. In some systems, they will be forced to discharge. In some systems, those that are undercharged will now be allowed to receive more charge for now the system to equalize at a specific voltage. That is, if it's meant to stabilize at 14.4 volts. So again, this absorption stage is normally critical because if, for example, your system has been designed, for example, at bulk stage we shall look at the different voltages. If your system has been designed to charge, for example, at 14 volts or 13 volts at the bulk stage, at the absorption stage, the voltage will drop. Whatever the system will be picking from the panels or the power source will drop so that you avoid overcharging now the battery pack. So in the float stage period, the intention of the float stage period is to ensure that the battery is fully charged, but it's not overcharging. So in this stage, once the system, and this is normally when the SOC is at 100%. So once the system determines that the SOC is 100%, the controller will lower the voltage into the battery. It will lower it to a very safe voltage to ensure that, or to compensate for self-discharging. So self-discharging normally happens when the internal resistance of the cell happens, chemical reactions, internal resistance and such effects normally happen within the battery itself. So it normally self-discharges. So after the battery is fully charged, the controller will lower the intake voltage to save low voltages to compensate for self-discharging and small loads. And this is meant to keep the battery fully charged without damaging it. So the essence of the float stage is so that if, for example, the battery has reached 14.4 volts for a 12-volt system, and it's not yet evening, so there's still enough sunlight to keep sending voltage into the battery, the system will not cut off charging completely. It will keep allowing a small amount of voltage to now continue trickling into the battery to ensure that between the time when the battery records a full SOC and the time when there's no power source completely delivering charge current, the battery is maintained at that maximum level of SOC. That's the essence of a float stage charging period. And it's essential because for some systems, for example, if you're not utilizing your system and probably during the morning or during the start of the next charge cycle, technically, you've not depleted your system, the battery will hold power at 100% SOC or 98. But if the inverter is too primitive or the charge controller is too primitive to notice this, it will cut off power completely from the it will cut off the source of charging power completely. Essentially, it's not supposed to cut it off completely. It's supposed to lower or reduce the charge voltage so that it's not coming in too much and the battery is maintained at that particular stage. So it will just be sending enough voltage and current to keep the battery active during that 100% SOC. Now, these are the three main stages of most battery packs or battery types, but we want to look again at an extra stage called the equalization stage. So in the equalization stage, it's mostly utilized by the lead acid batteries. I'll have to confirm the other chemical types if they normally have an equalization stage or an extra stage after the float stage, because for lead acid, the equalization stage means that you're sending in more voltage than even the battery can handle normally, technically, so that the internal chemical structure of the battery is activated. So let's explain the equalization stage also. So in the equalization stage, we've said that we will be sending a controlled periodic overcharge for the lead acid batteries. So this is normally mostly utilized by lead acid batteries, not the other types of batteries. Now, this overcharge means, for example, if our batteries are supposed to, the lead acid batteries are supposed to charge with, let's say, 13.8 volts, for example, I'll explain now the different charging voltages needed depending on the stage now per battery type. Now, for example, a lead acid battery is supposed to charge at 13.8 or 14 volts. At the equalization stage, happening after all the three stages have happened. So the first stage in a lead acid battery, let's say that the bulk stage has happened, the absorption stage has happened, the flow stage has happened. So after a period, for example, all these three stages have happened, after some time, not once or not twice, probably let's say after 10 charge cycles, your system, your intelligence system is supposed to subject your lead acid batteries to an equalization stage. And this means that for an unprogrammable system, this won't be achieved. But for the programmable systems, in the equalization stage, you send, for example, let's say 15 volts, and it's not a very short period, so as not also to damage the cells. So the controller will raise the voltage higher than usual for a short time, and this purposefully gases the battery. So for lead acid cells or batteries, as we will explain in the next session, gassing causes bubbles within the battery pack, and these bubbles will stir the electrolyte. It will when the bubbles form, when they rise, they cause some movement of electrolyte, and during that movement, the electrolyte will break down the crystals that have built up on the plates of a lead acid battery. So if you look at a lead acid battery that has not been gassed over a period of time, you'll find that on the plates there's something white that has formed over a period of time. So so in most systems, when you when the crystal forms, it means that now the charge capacity of each cell is being reduced. So to prevent that from happening, you need to do an equalization stage charging for lead acid batteries periodically. If you can do it manually, you do it once, or if you have a programmable system, you program it, and it does the equalization stage. Now, in our next session, let's look at now the battery types and how the different charging stages, the voltages of the different charging stages in the different battery types, and the effect of not following these charging stages for the batteries. Now, before I break it up, or before I move on to the next video, it's essential for you to know that a charge controller is supposed to be able to understand all these three different stages in relation to the battery type. And in some cases, for the primitive systems, a charge controller is not built with this program in it. The charge controller will only be built to understand that there is a X amount of voltage coming from the panels, and I'm supposed to release X amount into the batteries, and that's it. That's all it will do. It will just prevent you from sending too much voltage or and even current actually into your batteries. That's all they do, the basic charge controllers. So for the advanced charge controllers, these programs come inbuilt or pre-programmed by the manufacturer, and what you do as a technician or as a system owner, what you do now is to ensure that you link your battery, or you program the charge controller or the inverter to understand that you've linked it to battery type A, B, C, D, or E. That's all you do. The system itself will now know that because the technician or the end user has confirmed that they are using a lead acid battery, I'm supposed to shift my working to do these charging stages for a lead acid batteries. If you link it to a lithium ion battery and you inform it by keying all that information, they have options for that. The charge controller will now change the charging stages to conform with what a lithium ion battery needs. And so in our next session, we shall look at now how the different voltages vary, how the voltages, how the different voltages vary for different batteries, and apart from the voltages, the effects of not following the charging stages in your battery bank or in your solar PV system. So I hope up to there now, I think you now have a brief, I can say now, an established idea as to why the communication protocol is important. So if a communication protocol between the battery and inverter is not well established, your charge controller will just be sending one category of voltage all throughout the battery's life cycle. So your charge controller could just be sending, like if you've linked it to a charge controller that can only release 14 volts, for example, that charge controller will only be releasing 14 volts, and that is also if the panels are generating that much, because some systems are normally even sized in such a way that they cannot even release the maximum amount of voltage that the batteries can peak. So if your system is not sized enough to ensure that the charge controller can pick all these independently, that means that the communication protocol, even if it's there or not, the batteries will not be being served by the charge controller as properly as they should. And that also means that the charge controller, the inverter, or any other communication or any other component has to have a proper communication structure between them, so that if, for example, the batteries are at absorption stage and the panels are capable of releasing bulk stage, the inverter can pick the absorption stage voltage, and then the extra can be sent to the loads directly. So those little bits of communication. That's why I say that the first channel of communication is normally very primitive and won't. Basically, the channel 1 communication protocol will not allow you to do most of this. It will just allow you to do probably bulk stage and absorption stage. And in most cases, even that first communication protocol does not even know whether it's doing either bulk stage or absorption stage. Technically, it will just be releasing a certain voltage based on what the system is generating. So let's look at the different battery types. This family, they share the same battery chemistry and they differ in architecture, internal resistance, electrolyte behavior, and allowable gas pressure. Now, there are a few considerations that we normally take in determining the charge profiles for this particular family. So the first consideration is temperature compensation, and the charge profile is developed for room temperature, 25 degrees, not percent, but 25 degrees Celsius. So the battery profile, the charging profile has been developed at this temperature, room temperature. But because we are not existing in a perfect atmospheric environment, so the temperature will keep changing because we do not exist in a controlled environment. The temperature will keep changing even from room to room or region to region. So temperature compensation. Now, temperature compensation has ensures that we design our system, our charging profile in such a way that for when the temperature is cold, it will also affect the battery's internal temperature. So that will require a high voltage to charge. And when the temperature is high, it will also raise the battery's internal temperature. And so the battery will require a low temperature to charge, irrespective of the stage, even if it's the bulk, the absorption, or the float stage. Temperature compensation is important. The second, so you have to take into consideration that a good charging system will have to include a temperature sensor in the communication protocol to ensure that it's sending the right voltage capacities at every particular stage of the charging profile. So a battery that is being charged blindly, in some cases, it will affect its long-term lifespan because, for example, in rooms where the temperature, the room temperature is always way above 25 degrees Celsius at any given time, and this battery is charged at, again, high temperatures at almost at all given times, uh, the internal chemistry of the battery will keep getting affected, and over time you'll realize that now the lifespan is becoming shorter and shorter over the period. The second consideration is the acceptance rate. The acceptance rate means that when a battery is at a certain state of charge and a voltage level, the amount of voltage it can take in at that particular point normally differs when the voltage either increases or decreases. So for example, if a battery is approaching the full capacity, both the voltage level and the state of charge, the amount now of voltage and the current has to be lowered to prevent, because now the internal resistance of the battery is high. So if you keep pushing voltage and current with this in the same high capacity, it creates heat. And once full, all the excess charge will be converted into heat and gas, and this damages the battery itself, the internal structure of the battery. Depth of discharge. Now, it's important to know that lead acid batteries are effectively managed when kept at high depths of discharge. And in some of our previous sessions, we've said that this high depth of discharge is normally 50% and above. For a lead acid battery, always maintain at least 60% DOD. So, for example, if you size your system and the client is going to use a lead acid battery, the FLA or the gel battery, ensure that you size your system to never go to be depleted beyond 50% for a very, very, like on the list. Like when the battery is at 100% in the evening, size your system in such a way that by the time tomorrow morning comes, the battery will not have gone below 50%. That's what this means. Because deeper depth of discharge causes stress on lead acid cells, and when internal stress is constant, it shortens the lifespan of the battery pack. So the charger allowance. So the unprogrammable charger will never fully manage a lead acid battery effectively through all the charging stages of the charging profile. So this statement means that if your charge controller does not have inbuilt programs or it's landlocked, can't allow you to add any extra programs in the stage, in the charging profile, to manage the charging stages. Your charge controller basically will just have this battery in one particular state, in one particular charge stage for its entire lifetime. And we've explained that when your battery is kept at that single stage in its entire lifetime, the lifespan is lowered. For flooded lead acid batteries, this is the recommended charging stages. So first we start with the bulk stage, and then we go to the absorption stage, and then we go to the float stage. So this is the normal recurring charging profile. And then periodically between uh, in some systems, they normally encourage to as little as 3 or 4 weeks. In some systems, they say 1 to 3 months. So it will really depend on if the manufacturer has also included that information, follow what the manufacturer has recommended. In some systems, you can do it every 3 to 4 weeks or 1 month. And in some systems, you can go to all the way to 3 months, do it once every 3 months. So it's essential for maximum longevity as it prevents stratification and sulfation. So for students, I want you to go and read about stratification and sulfation independently, understand how this affects the lifespan of the flooded lead acid batteries. For absorbed glass mat and the gel batteries, this is the preferred charging stages or in the charge profile. So we start with the bulk, we go to the absorption, and we go to the float. So it's essential for the maintenance-free operation, because with gel batteries, basically they are normally marketed as maintenance-free. You just install them, leave them. But that will also depend on the other subcomponents that you link it to. If you link it to a good charge controller, you are good. If the charge controller that is will allow you to program so that it does all this, goes through all these stages continuously, you are good. But if you link it to a charge controller that does not have these, then it lowers the actual lifespan of the battery, because it will keep that battery in one charging stage for its entire lifespan. So maintenance. So when you do this, you are controlling the gas production and thermal runaway from the battery, from the AGM and the gel batteries. So this essentially means that the first category of charge controllers, I normally call them the blind pilots, are a bit, we could say, dangerous or poor for larger systems. So these are the charge controllers that do not come with any form of programs in them. They just basically have electronics that allow them to filter the voltage coming from the panels and release the required amount into the batteries. So these ones that are dangerous for bigger systems, reduce the lifespan of the system by far. And again, apart from being dangerous and poor, the return on investment of the system. These are some of the reasons that you are supposed to look at when now you are, by the time you give your client a bill of quantities, you look at how long this client will take with this system before they recoup their investment. So if you combine a good battery bank of whichever type, either FLA or AGM or gel, but you combine it with a charge controller that cannot communicate and ensure that these batteries go through these charging stages effectively, you will if a battery has even been marketed to go for at least 3,000 charge cycles, you'll realize that it will not even hit probably 2,500 while operating at both SOC and SOH still at 100%. So you'll find that the battery will already have lost at least 10% or 20% SOC and SOH by the 2000th cycle, which is bad for you as a technician. You might even make the brand look bad, but it's because probably there was no proper communication between the technician, the user, and the brand. So for this case, let's now look at the voltages themselves now. I know it's been a very long session by the time we get to the voltages. So let's look at the voltages and see how the voltages now affect the performance of the different battery types. We are still on the lead acid family. After that, we'll go to lithium ion, the lithium family now, sorry. Yeah. Now, the first category, the flooded lead acid battery types. So we are going to deal with the 12-volt system. And I said, when you change the voltage capacity of a pack, this whole information will change, the charging profile. But because most of our students will be dealing with essentially the 12-volt system at level 3 and 4, they'll stick to this information, and then we'll update it once we start learning about bigger systems. So for the flooded lead acid cells, batteries, the first stage, the bulk stage, the charge controller is supposed to be set either manually programmed or pre-programmed to charge between 14.6 and 14.8 volts. That is the voltage first. Now, the maximum current allowed, this will be given by the manufacturer, depending on how he's packed the cells within the battery. So the maximum current allowed, now this is the C rate. And then these this charging stage is normally recommended between when the battery is at its lowest state of charge to around 80% or 90% state of charge. And this will vary depending on the manufacturer. Also, the manufacturer can specify whether to do it from the lowest SOC to 80 or the lowest SOC to 90. They are not set values. So the second stage, the absorption stage, we change our voltage, we lower it now from 14.6 to 14.8 to 14.6 to 14.4 volts. So here we use a low current. We can use even half the maximum allowed current, and we are raising the SOC. It's recommended to raise the SOC from 80% to maximum SOC, that is 100%. Or if you cannot have this information predetermined, if the battery does not have, if there's no communication protocol between your inverter and battery, or your inverter and charge controller that can determine the SOC, not the voltage level, the SOC, you can manually program your system or do it yourself and ensure that the battery is charging between 2 to 4 hours maximum after it hits the 80% SOC. So this will also be possible if you now start monitoring the voltage level. So you yourself can do a monitoring. You can have a separate gadget to monitor the voltage levels, or you can do it. There's a calculation that can, when you combine, there are a few components that if you combine, they can tell you the battery's SOC. So in any case, if you don't want to go all through that, you can do it at least, you can manually program your charge controller to do it at least 2 to 4 hours maximally. The third stage now is the float voltage. This is after the battery has hit the 100% SOC state of charge. So here, we lower the voltage again from 14.4 to at least 13.5 to 13.8 volts. So again, here we utilize low current, and the battery itself will keep shifting between 95% to 100% SOC. If the battery doesn't do it automatically because of the internal resistance and discharging, you can keep monitoring this, and it's a continuous process. So that's why we said if the system is advanced, the communication protocol will do all this heavy work for you. Your work is just to connect, feed in the information, and leave it. And then we have the equalization stage for the flooded lead acid batteries. So in this stage, we raise the voltage to 15.0 to around 15.5 volts. And this you'll have to do it independently, manually. If you don't have a charge controller that can determine this, you'll have to do it yourself manually. You go and increase the charge voltage that the charge controller can allow to go through from the panels or from the grid into the battery. So you raise it to around 15 to 15.5 volts. it's recommended you use low to medium current, so you can use the half the battery's allowed C rate. And then it's recommended that you do this process every whenever the battery is at above at least 80% SOC. That's the recommended practice. You do it when the battery is at around above 80% SOC. But there are different texts. Some are saying you do it at around 50, some are saying you do it when the battery is full. So I haven't confirmed in which state this is actually preferred to be performed. Some are saying you do it even when the battery is as low as 40% for the flooded lead acid. So I'm not limiting you, but what is so the frequency will depend on the usage of the battery and the specifications guideline. So you can do this equalization at least, some are saying you do it at least once every month. Some are saying you do it at least once every 3 months. But what is certain is that how you are utilizing your system will determine how you do this. So if your system is subjected to frequent charge cycles, you are also supposed to do this frequently. If your system is not subjected to frequent charge cycles, you do it less frequently. And the other aspect you are also looking for is how deep the discharges happen. So that will also guide you. If your system is subjected to extreme deep discharge cycles, do it more frequently. So the flooded lead acid battery is made up of liquid sulfuric, which is flooded over the plates. When you look at it, ukitingisha, you'll see the actual sulfuric acid, and the plates have been arranged one after the other from terminal to terminal or from pole to pole. So these batteries need a higher bulk and absorption voltages to break sulfate crystals, and they release gas safely through the vent caps. So this is also something to note. I think if you are using lead acid batteries, you should also ensure that you monitor the vent caps and ensure that they are always open. Because for a solar system, you install your batteries and you disappear. So if you do not open the vent caps, or if the vent caps get closed, the gas will feel it might bulge out, because it keeps forming gas whenever the charging process and the discharging process happens. So equalization is essential for lifespan. We've talked about it over and over. Now, wrong charging profiles for FLA, apart from, so let's first understand what a wrong charging profile for an FLA is. For example, you have a charge controller that is always delivering 13 volts, assuming you have a charge controller that never hits these voltages. It's always stuck at 13 volts. That means that if the SOC of this battery is at below 60%, this battery will be constantly assuming that it's on float stage charging cycle, which leads to undercharging. And this undercharging is the reason why we undercharging, sulfation, and reduced capacity. So whenever you undercharge this battery, it means that at any given point, not all the the battery does not experience chemical reaction in entirety. And that leads to sulfation and reduced capacity. When now the reduced capacity happens because the capacity, the actual capacity of each cell starts shrinking, because the chemical has bonded on the plates. So either because the actual charge carrying electrolyte is now not available because it's been bonded on the plates of the internal plates of the battery. Now, if you subject this battery to a poor charge profile, let's say bulk continuously, you are doing overcharging. So, for example, if you always connect it to a charge controller that is continuously charging at 14 volts, for example, 14.5 and above, and this is constant, that is overcharging. And when you do overcharging, we have excess chemical reaction, which leads to water loss or electrolyte loss. So for the FLA, these are the required charge profiles. And for you to achieve the equalization stage, you always have to find a way of pushing your charge controller to these voltages. So if you have a charge controller that cannot deliver these voltages, you'll have to find a grid connected charger. We have got grid connected chargers that have been built specifically for this purpose. You can connect your battery to a grid charger that has got programmable features for you to push the voltage to 15.5 volts. And even the current, you can modify the current. The details will be on the manufacturer's specifications. You can charge at half the C rate for at least 1 or 2 hours or 3 hours, and frequently every month. We have said between 1 to 3 months, or depending on the battery use. So the second type of battery is the absorbed glass mat battery, or the commonly known as the AGM battery. So for a 12-volt system, at the bulk stage, we can push between 14.6 to a maximum of 14.8 volts at a very low to medium current. And these current settings, you get them on the manufacturer's specifications, whatever the manufacturer will specify, because the manufacturer, depending on how they've packed their battery and the internal architecture, they'll tell you what current to use. And it's normally medium to low, never the full charge current for these particular batteries. For the bulk stage, you can utilize the bulk stage when the battery is at its lowest SOC to at least 80% SOC state of charge. And then from this stage, we move to the absorption stage. So at this stage, we lower the voltage from 14.6 to around 14.4 volts. Again, we are still utilizing the lowest to a maximum of the, not low, so we will use low to medium current. This information will be available from the manufacturer. We'll use the absorption stage to push the battery from 80% SOC to 100% SOC. And this typically has to occur between 1 to 2 hours, or if the process of getting from 80% to 100% SOC will be shorter, that is recommended. When you subject it to absorption for longer period, it also affects the internal chemical structure of the battery itself. And I didn't want to go too deep into that for now. For the float voltage, once the battery has hit 100% SOC, we lower again the voltage from 13.8 to 13.5. And then we go now to the lowest current and maintain our battery state at 100% SOC. And this one can be continuous as long as the battery is full. So if you're utilizing your battery, an AGM battery, if you're actively utilizing it and it's charging at 13.5, that is, you are undercharging it in that case. Now, I think from this point now you start understanding the reasons why even the voltage themselves have to be controlled for this system to charge effectively. So for an AGM battery, there's no equalization, because equalization causes dry out. But if you have a technician who has analyzed the system and understands it, the maximum voltage you can push into an AGM battery for equalization is normally 15 volts maximum. And according to the little research that I've done, don't do it for over 1 hour, maximum 1 hour, and it should be very not as frequent as the flooded lead acid batteries. You can avoid it altogether for this system, there will be no issues. The equalization part. So these batteries are characterized with low internal resistance, hence they heat up quickly. So because of the low internal resistance, if you push very high voltages and currents, they heat up very quickly, and you risk losing the battery within the shortest. They are sensitive to high voltages and currents, so you always also take that into account. So if you push more voltage than what it can handle, you risk losing it within the shortest period of not knowing what's happening. Number two, yes, overvoltage and leads to drying up and permanent capacity loss. This drying up normally happens because of the gassing. The electrolyte escapes, and since the electrolyte is what holds the charge, you suffer permanent capacity loss. So the wrong charging profile in this case will cause gassing, undercharging, and sulfation for the AGM batteries. The next battery is more common compared to AGM, and in the current Kenyan market for solar, most people don't. Okay, I won't say most, but most of the systems I've interacted with normally utilize the gel battery, and so here is where now the gel and the flooded lead acid. So let's take a keen look on the gel and the flooded. Sorry, we have already looked at flooded lead acid. So let's take a keen look on the gel batteries. Most common battery type locally used in our market is this gel battery. And here is now something that I think at this point, most technicians should take note, because it's something that I also learned after doing a little bit of research, not knowing that some systems might be punishing the batteries unknowingly. So the gel battery, first of all, let's look at the voltages at the different stages. So at the bulk stage, the gel battery should not be charged with anything above 14.2 volts. Actually, some texts are saying nothing above 14 volts. And you use the lowest charging current. Actually, this charging current should be, I think some manufacturers cap it at the, not even half, at the a quarter of the C rate. Some of the specifications that I have. So we will look at them independently, but some are saying you cap it at a quarter of the C rate. Now, I was trying to do the calculation and see how long it will take, and then I realized it's a bit complicated for now for this stage. So we'll just use the lowest current or whatever the manufacturer has specified from their specifications. So at this stage, we will lift the battery from the lowest state of charge to around 80% state of charge. Some are saying to at least 60%, which is okay. Now, the funny thing the issue I was having is that if you are not recommended to deplete it below 60%, and some manufacturers are saying that this bulk stage is used for this system between the lowest to 60 or 80%. It means that for the gel battery, the longest time a gel battery should spend during the recharging part of the cycle is at the absorption stage, because most of them will not be depleted below 60%. So from 60 to 80% will take a very short time, and you move it to the absorption stage. Now at this stage, we also lower the voltage to 14.0 to around 13.6 volts. We use the same low current, and we lift the battery from the 80% SOC to 100%, or we leave it at this stage. Some manufacturers are saying you leave it at this stage, 14.0 to 13.6, and then you leave it at that stage, keep charging it at these. Some manufacturers are not commending or are limiting you to the absorption two stages. I mean, the bulk stage and the absorption stage only. They're not taking you to the float stage. But for those who are taking you to the float stage, they're saying you lower the voltage again by 0.2 low current and keep it here. So it's either at absorption stage or a float stage. So a gel battery should be maintained between 13.4 to 14 volts at any given time. Now that is after you've understood how to know the SOC of your system. So if it does not have the RS protocol or the CAN bus protocol, I I don't know how you'll now be managing this, because I've also realized it after doing a little bit of research, which also informs the reason why most gel batteries do not go the lifespan that the manufacturer intended. Because I've actually um, witnessed a system that the gel battery is charging at around 14.6 volts, and it's constantly at 14.6. Whether you come in the morning or in the evening, it normally varies between 14.3 to 14.8 volts. So for this system, we do not have any equalization. So here we avoid equalization. Once you install it and you maintain this, if your inverter is inverter and battery have got a communication protocol that can maintain these charging stages. Never do equalization for a gel battery. Now, the gel battery utilizes the sulfuric acid mixed with the fumed silica to form that thick gelatinous paste. If you crack one, you'll realize that it's not as liquid as the flooded lead acid. It's something like like light mud or paste, that gelatinous paste. The disadvantage is that when you change the when you have a slight variation of even 1 volt at the wrong charging profile, you are weakening the battery. So that means that if, for example, it's at a float stage here from 95 to 100%, if the battery is at 95 or 100% SOC, and you change this voltage to 14.2, you are weakening that battery. Technically, that's what this statement means. So at each particular charge stage, ensure that you are pushing the recommended voltage into the battery. If you push any extra, you are weakening that battery. So in any sense, for a gel battery, once it's full, you are supposed to have a proper system that will notice the voltage level, compare it with the SOC. If it's full and it's 100%, I'll even recommend you to just keep it away. Have a system that can disconnect it completely and avoid even float charging it. Just have a system that can disconnect until the next charge cycle starts. It needs the slowest, most controlled charging profile environment. So, and this is also, the environment will also affect the temperature, humidity, the load that is being drawn out of it. So it's the most sensitive, and a wrong charging profile will cause internal voids, which will cause number one, reduced capacity, and number two, permanent damage. So I'd like my students to go and find out some of the 10 things that are different between the gel battery and the AGM and the FLA. So I want you to list at least 3 that are different here, 3 that are different with the AGM, and 3 that are different with the FLA. Combine all of them here. And so in our next session, we shall see how mixing these charge profiles affects the battery performance independently. For example, if you have an inverter, it's supposed to charge an FLA battery, and you connect it to a gel battery, we shall see how that affects the batteries. Or if you have an inverter that was programmed to charge a gel battery and you're charging an AGM battery. So we shall just look at a slight comparison before we proceed now to our next session. Now, at this stage, this has been very fast. I've not really, there's a lot of information on this, and if you try to dive deep, you will also again have to take sub branches. So I didn't want to go so too deep into it. I just wanted to introduce it and at least have students understand that there's the aspect of sizing, you size correctly. There's the aspect of installation, install correctly. But even before you get to installation, you should know that when after sizing, when now you go into the market, just based on this information, you'll realize that some components will never be compatible. A gel battery will never be compatible with a charge controller that cannot understand this information and send voltages depending on the actual charging state that battery is in. So if you're a technician out there and a client approaches you and tells you that their gel battery is not yet even 3 years in, but it's already failed, the first thing you're supposed to look at is how the charge controller or the inverter is sending, like at what voltages is that inverter or charge controller charging that battery. And in most cases, you'll find this with the gel batteries. So if the gel battery is failing earlier than the intended life cycles, go straight and see if the bulk voltage or absorption voltage or float voltage have not been pre-programmed into the system. You already now have your answer. And this was just a very, very light, walkthrough through this. The intention was for students to understand that communication protocols between batteries and inverters, or batteries and charge controllers, or all the three, is important. Now, because the RS protocol and the CAN bus protocol is a little bit too complicated even for me. I leave that to those who are interested in doing their own research. You can go and research more about the RS protocol or the CAN bus protocol. It's more of electronics, and students of electronics might find it easier. For me, I think I leave it at this stage. The only thing I'm going to add is now how the effect of now mixing and matching the charging profiles, and how we can ensure that when we are sizing a system, we shall do a simple example of how to size a system and ensure that if we do not have the components that are communicating to each other, how do we ensure that we size a system that can at least respect the charging profiles, even if the components are not listening or communicating to each other. So that will take a little bit of time. We have to do a little bit of research on that, but thank you for that. If we take a different branch after this, don't worry. I'll keep these videos in a proper playlist on YouTube, and then I can just be sharing the title and you just follow along. That is the advantage of YouTube. For those on TikTok and yes, TikTok, because we are saving this on both YouTube and TikTok. For those on TikTok, I think you just have to follow along. There's no way. I don't think I can arrange playlists on TikTok. I've not met that feature. If I meet it, I'll arrange them. If I don't, then YouTube, we will utilize YouTube to arrange our playlists on how we build our learning sessions slowly by slowly. So thank you to all those who've listened to this point. I'm sorry for the if you've been confused at some point because of how the delivery has been, kindly just share, and I'll always be glad to revisit and review some of the work. Asanteni.